More. I'm going to introduce you now. You're ready to go?
Yep.
Okay. So thanks, everybody. It's my great pleasure to introduce Mor Geva. She's a professor at Tel Aviv University. That's why she was not able to make it today. And she works broadly in NLP on a lot of reasoning and capabilities of LM tasks. And that's what she'll be telling us about today. So please take it away.
Thank you. Great. Yeah, thanks so much for having me today. And I'm sorry I could not attend in person. Anyways, I will talk today about latent reasoning in large language models. Right. So the ability to reason has long been a hallmark of artificial intelligence. Even if we go back to the 50s, researchers already then described systems that receive as input a set of sentences or facts, and then derive some expressions or theorems from them. And reasoning has all kinds of shapes and forms, but essentially it's the ability to take multiple pieces of information and conclude something from them. So, for example, in the case of compositional reasoning, a system could be given these two facts: the singer of superstition is Stevie Wonder, and the mother of Stevie Wonder was Lola, and then derive some conclusions from that. For example, that the mother of the singer of superstition was Lola. So moving forward 60 years, today we have transformers and people train large language models on large scale of data. And these models know a lot of things. And in terms of their reasoning abilities, well, it seems that they do pretty well. So if we give such a complex query to a language model, so who's the mother of the singer of superstition? So typically, large language models today has all the information to answer such queries. And typically we'll get an answer like that, so pretty lengthy. And if you notice, so models do not typically output the final answer immediately, right? So they first generate some necessary information. So the singer of superstition is Stevie Wonder. And then when they actually provide the final answer, so Lola in this case, the model has this information in context, right? So in some sense, reasoning is being done over the input space or the vocabulary space. And what exactly this means, so if we restrict models to just output the final answer, right? So for example, like this, right, we instruct the model provide a short final answer to the following question without any extra text. So actually, it's pretty hard to make models just to output a short answer, but let's say we've made it, then it forces them to conduct the reasoning latently in a single inference path. And this actually caused, in many cases, to performance go down, right? So typically, when we do that, we won't get the correct answer. But there are still success cases, right? So here I took the exact same prompt, and instead of feeding it to ChatGPT, I used Claude, and it got it correctly. So what exactly is going on here? Like, are these models capable of latent reasoning? And if so, how do they solve such tasks? So going a few years back, it seems that at least in terms of the architecture, models are able to do deductive reasoning to some extent. So Clark et al. At 2020, they took a relatively small transformer model and trained it on synthetic data like this. So on a bunch of facts and rules, and they saw that models can deduce all kinds of expressions from that. And very recently, concurrent to the works I'm going to present today, actually, so research has showed basically that, again, if we take a relatively small transformer model and train it on structured data, then we can observe this ability to deduce compositions, but only in the in-domain distributions and under some conditions. But what about large language models that we use, day to day, that are trained on real data and they are large scale and so on? So in this work, I will present two recent works that we published in attempts to answer all these questions. The first one will focus on exponential evidence of latent reasoning in Llama 2. And then in the second part, we'll dive deeper and explore the limitations of this latent reasoning in multiple language models. Right. And the problem setup we are going to consider is compositional reasoning, or if you would like, just two-hop queries. For example, like this one, so the spouse of the CEO of Google is, right? So it basically composes two facts. And when we humans solve such queries, we typically solve them in a backwards manner, right? So we start from resolving the CEO of Google being Sundar Pichai, and then we resolve the second hop, right? So Sundar Pichai is like the bridge entity, and then we resolve the second hop about his spouse being Angelo Pichai. And yeah, so when models answer such queries, then we feed them right as input, and we represented them as a sequence of token embeddings. And throughout the talk, by the way, I'm going to assume or focus on decoder-only autoregressive language models. So we assume that the answer is always obtained from the last position of the input. And then the question is, well, how do models solve this, right? And they could solve it in multiple ways, right? One way is like we do, so in a backwards manner. But there could be other ways, right? It might be, for example, that there's just strong correlation between the CEO of Google and Angeli from the pre-training data. And so the model doesn't really need to do this backwards reasoning. Or there could be other information somehow that connects between Google and Angeli. Yeah, so we basically want to see how models solve this. And the first work was done with collaborators at Google DeepMind and UCL. And basically what we did here, we broke down this question into two research questions. The first is, well, when we feed such two-hop queries to language models, do they actually solve the first hop when processing the complex query? And the second question, well, assuming they do, so how well or to what extent they utilize this first hop resolution for answering the second hop? And for our experimental setting, we constructed a large-scale data set of 45,000 two-hop queries, which cover 52 types of fact compositions. And we experimented with the Llama 2 family of 3 different sizes, so 7B, 13B, and 70 billion parameters. And we focused on cases or on queries where the model can answer each of the hops, right? So the model basically has all the knowledge it needs for answering the question. And so we focus on its basically the ability to compose these facts or reason in its latent space. Great. Our high-level approach is going to be the following. We'll first introduce an internal entity recall score that basically measures how strongly models resolve the first hop. Then we'll introduce a consistency score that measures the utilization of the first hop for answering the second hop. And finally, we will conduct a test where we will increase the entity recall score and check if it also increases first hop utilization, which in other words, it will be a test for the second hop resolution or the latent reasoning that we are after. So starting from the first question, we're going to introduce this entity recall score, and we're going to do this as follows. We're going to look at the hidden representation at the last position of the first hop, so at the position of Google in this case. And so the reason for looking at this position is because it's another aggressive model, and so the last position is the only position that covers like all the information of the hop. And then we'll sort of like inspect the intermediate output representation in this hidden state. How we are going to do that? Basically, we're going to apply the same operation that we apply at the last layer. of vocabulary projection, but to this intermediate state. This is also often called logit lens. So basically, we take this X, we project it to the output embedding matrix and take a softmax. This gives us a probability distribution over the vocabulary. And then we're going to look at the probability or log probability of the bridge entity according to this distribution, right? And it basically can tell us how strongly the model thinks or recalls the bridge entity while it processes this two-hop query. Now, this score by itself, it doesn't tell us a lot. We don't know really what's high, what's low in this case. And so we're going to do a very simple test. We're going to compare this score for two different prompts. The first prompt is the original prompt, where the prompt actually describes the bridge entity. And the second prompt will be a counterfactual prompt. So we will change it only slightly to describe a different entity. So here, for example, we changed the CEO of Google to the COO of Google, which is a different person. And so basically, we are checking if changing the prompt such that it describes the bridge entity also increases its recall. And here we can see the results for Llama 7B, 13B, and 70B. The x-axis shows the layer of the model, and the y-axis shows the portion of examples where changing the prompt such that it describes the bridge entity also increases entity recall score. And so we see here two trends. The first one is that across all models, right, we see that for the vast majority of queries, we do see this increase in entity recall. And the second observation is that this behavior basically scales with model size, right? So if we would look at the maximal value for each model, you will see that it gets higher and higher, right? Yeah, so we basically take this as an indication for a resolution of the first hop. And right, now we move to the perhaps more interesting part. Like, okay, so let's say models resolve the first hop. Do they actually use this resolution for answering the second hop? And to answer that, we introduced a consistency score that basically measures the similarity between two output distributions. The first one is the output distribution obtained for the two-hop query. And the second distribution is obtained for basically the same query, but where we resolve the first hop for the model, right? So we have the spouse of the CEO of Google and the spouse of Sundar Pichai, and we basically want to see how similar these distributions are. And the intuition here is that the more similar these distributions are, it means that the model utilizes its resolution of the first hop in the two-hop query more similarly to how it uses the bridge entity itself. And so how we're going to compare between these two probability distribution, basically with the symmetric cross entropy score. Yeah, and just like a side note, we also experimented with accuracy and observed similar trends. So yeah, but we thought this is more informative metric. Right, so we have our entity recall score for measuring the first hop utilization. We also introduced the consistency score for measuring utilization of the first hop. And now we're going to do our test to basically see if there is like a second hop presence. So how we're going to do that, we're looking again at the same hidden representation at the last position of the first hop, and we're going to do a very simple reparameterization trick. So we're going to write x as a function of alpha. And this new vector is basically defined as the original vector x plus some step size towards the direction that increases entity recall. And once we do that, and this direction, of course, we can compute during inference. So once we do that, the consistency score also becomes a function of alpha, and we can calculate its derivative at alpha equals 0. So we are basically looking at how the consistency score changes And we specifically look at how it's being changed when we change the entity recall score. And a positive value in this case would mean that an infinitesimal increase in entity recall also increases consistency, which means that the model utilizes the first hop. And a negative value means that an infinitesimal step towards the direction that increases entity recall will decrease consistency, meaning that the model does not utilize the first hop. Great. So the results. So this plot shows the results for randomly initialized model, right? So it's not a trained model, it's random model. And the x-axis shows the layer, and the y-axis shows basically the portion of examples where we observed an increase in consistency score when we increased the entity recall score. Right, so if we, so basically we see here like it's completely random as expected, right? So 50% chance. Now we will see the results for the trained models. So this is 7B, 13B, and 70B. And we can see here two trends again. So first of all, across all models, we see rather weak signal, right? So for some portion of the queries, which is statistically significant above half, above random, we do see this positive signal that increasing, like helping the model to recall the bridge entity also increases its ability to resolve the second hop, but it's only weak. And also it does not scale. So the maximal score across models is roughly the same. Right, so conclusions so far, we saw a strong signal for first hop resolution. We saw also that it does not translate to strong signal of second hop resolution, but rather weak evidence, which does not scale. And we took it as a suggestion that there might be just more dominant pathways for solving these queries. So it might be that for some portion of the queries, the model does have this pathway, but it's definitely not the dominant one, and maybe there are other pathways. So now let's dive deeper and explore the limitations of this latent reasoning pathway that we discussed. And this work was done at Tel Aviv University in collaboration with Google DeepMind and UCL. Great. And here we expanded our experimental setting. We also used like a much larger data set of 82,000 queries. But here we kind of focused on the queries where it's less likely that the model uses shortcuts, right? Or we try to focus more on the latent reasoning and not the queries where the model can answer using other pathways. So how we do that, we simply filtered out queries where the model can answer without some information, right? So for example, if queries where the model can produce the answer, like, but without, for example, mentioning Google or CEO, right? And we also constructed like two subsets of queries where the model provide the correct answer for the two-hop query versus incorrect answer. Yeah, and we also experimented with more models, including Llama 3 and PTL. Great. And the key tool we're going to use is Pathscopes. And the idea is basically it's basically a tool that uses activation patching, and it basically uses the model itself to translate information from its own hidden states into natural language. So how exactly it works. So let's say we have one inference path of the model, so Amazon's former CEO attended Oscar, and let's say there is some hidden representation that we would like to understand something about what it encodes or what it captures already during inference, right? So let's say it's the green one here. One possible question, for example, could be whether it encodes like CEO or whether it encodes already like the contextualized input, Amazon's former CEO, and so on. Right, so we take that representation and basically we apply some function. For our purposes, we can think about this just as identity function as we do nothing. And then we patch it into a separate inference path. And the idea here is basically to you define an input for the model that steers the model to extract or decode some information from the patched hidden representation. So for example, if we just want to see which token is encoded in that representation or token prediction, then we construct this few-shot demonstrations prompt that basically try to steer the model to map every token to itself or every hidden representation to itself in a way. And it might output, for example, in this case, Jeff Bezos, if the patched hidden representation already contextualized the input. Great. And this is the tool we're going to use. And first, we're going to use it for this first top resolution, right? So we'll apply it to the hidden representations at the last position of the first top. And basically, we want to see which entity is encoded there, right? Is it Google? Is it the bridge entity, Sundar? Is it the target entity? And so for that, we constructed this feature demonstrations prompt that basically has like subject and description. So think, for example, Leonardo DiCaprio, an American actor, Paris, the capital of France, and so on. Right. And these are the results. So we observed for a substantial, so this graph shows the portion of queries where when we did this patching, we managed to decode, we observed that the model decodes the bridge entity instead of the input entity. Right. And so we see that this happens in a substantial portion of the queries, both in the correct subset and the incorrect subset, which is nice. And maybe more interestingly, we also see that we can decode this information. We can decode this bridge entity when we patch the representation from the early layers, right? So here, each row shows the layer from which we take that hidden representation, and each column is a layer where we patch this representation, and we can see that the most bright cells are in the early layers, right? So what this all gives us is the following picture. Basically, when we feed such two-hop prompt, the model sort of like resolves the bridge entity in the early layers. It turns Google into Sundar Pichai, let's say. Right. And we had a bunch of experiments that I'm not going to detail here, where we also showed that this representation of the bridge entity propagates to the last position. Right? And for that, we use all kinds of techniques, including attention knockout, vocabulary projections, path scopes, and so on. And overall, we saw that pretty confidently that between 70 to 85% of the cases, we could like detect this propagation, both in the correct and incorrect cases. Right, and just to conclude this pathway, we also did the same analysis, but for the last position, from which we eventually obtained the prediction. And here we see the portion of queries where the model we could decode the target entity from some layer, where we could decode the target entity. And we see that here, unlike the previous plot, here we see a substantial difference between the correct and incorrect cases. So for the correct cases, for the vast majority of queries, we could decode the target entity, and these numbers are much lower for the incorrect cases. But the more interesting observation is that here we managed to decode the target entity only in the upper half of the layers. Right? So only after layer 16 in this model, but it's kind of consistent across all models we analyzed. So we have this image now. All right, we saw that the model solves the first hop, and then the bridge entity propagates to the last position, and finally it becomes the target entity, which is all nice. But one thing which is quite interesting here is the sequential nature of this process, right? The second hop resolution happens only after the first hop resolution, and we also see this quite nicely if we plot the distribution of layers where each stage happens, right? So for the correct cases, we see this very nice, almost linear line when concerning the layer, the mean layer. But when comparing this to the incorrect cases, we see actually something interesting. the first hop resolution and the second hop resolution, they sort of like happen later, or maybe even too late in a sense, right? So when we compare these means and these means, we see that this happens later. And also for some reason, the information propagation happens very early. But yeah, one hypothesis we came up with at this point is that maybe a lot of the failures, the reasoning failures, are just because the first hop is being resolved in a sense too late, right? And so this doesn't leave enough layers in a sense for the model to actually conduct the second hop of reasoning. And to test this, we did a very simple analysis that we called backpatching. And basically what we did is to take this later layer representation and patch it to an earlier layer. And in this way, we sort of like provide the model more layers to do the second hop of reasoning. And basically, we observed that this improves the ability of the model to answer these queries pretty substantially. So here you can see the improvement for the originally incorrect cases. And also, it didn't hurt at all the correct cases. So for any complex query that the model originally answered correctly, it still answers correctly if we provided more layers. But if it failed, then adding these layers can help a lot. Right, so to summarize, we saw an exponential evidence of latent reasoning in large language models. This is essentially a pathway that is prominent in cases where the queries are less likely to include shortcuts. The sequential nature of this pathway also points to a limitation in the computation of language model to perform latent reasoning. And finally, yeah, it's not really clear how dominant these pathway in like typical queries, right? It seems that it could be that a lot of the success cases maybe just be based on other pathways that do not really rely on this backwards reasoning that we humans do. And to conclude, I think that an interesting question to think in this context is, well, I mean, maybe the first question is like, how to build models that can perform reasoning in their latent space rather than their vocabulary space? I think this is an interesting question, and maybe I don't know, it could lead to models that reason better. But another question here is if we should be, right? Because probably there are a lot of advantages to the fact that, you know, maybe it makes them all more interpretable, or its reasoning more interpretable to us if it's expressed as a chain of thought, for example. Yeah, and that's it. I'm happy to take questions.
Any questions in the room? And I'll hand you a mic since the room mics aren't great.
Hey, thanks for the great talk. So it seems like a big assumption with using Logit Lens, and even with using some of these patch scopes type methods here, is that the sort of place where all the intermediate results of computation get represented is the same as the place where the model's predictions are actually going to get generated. And you can imagine, like, if the model was doing all of its intermediate reasoning in some subspace orthogonal to the subspace where all the tokens live, we wouldn't be able to find it with these methods. So do you take this as evidence that in fact all of the reasoning is going on in the vocabulary subspace, or do we need new techniques to figure out what's happening?
Yeah, so that's a really good question. I don't think we can the exponential evidence is basically for like the positive direction. Like, I think it's for, we do see that in very specific cases there is this pathway. So we cannot really say anything about, you know, if we would not observe any evidence, I think we could not like refute it. Like, it still could be using these methods. But yeah, like, I agree with your intuition. Yeah, it only provides us like a positive evidence, not a negative one.
Yeah, but I mean, it also suggests maybe some sort of story for how this capability evolves, that first you learn to do one-hop things, and then the one-hop things get pushed down in the network, and then they're accessible to the second hop. And do we know anything of that form about sort of how this behavior changes over the time course of training?
So the paper I mentioned at the beginning, let me scroll for a second. Actually, it's a lot of scrolling, so maybe not. But there was this paper, grok transformers, implicit reasoning, some combination of that, where they actually tried to trace this, but in a kind of synthetic setup. So yeah, it could definitely be interesting to try and do that in more natural setting. But yeah, I think, I don't know, some intuition I have is that sort of what happens is, at least in the failure cases, and I think that the backpatching experiment also shows this to some extent, is that once the model gets to the upper layers, it's hard to sort of like extract. Maybe these layers do not encode enough information for the model to extract it, so it sort of like needs the first layers. But yeah, it's kind of hand wavy.
Related to that, I just have a quick one. Have you also thought about this in the context of chain of thought, which gives the model a little bit more time to think about things if it's late in the layers?
Oh, definitely, definitely. Like, I think this is exactly, I mean, I think this is where my intuition comes from. I mean, if you think about I don't know, let's take, for example, the spouse of the CEO of Google, for example. If the model first produces, like generates Sundar Pichai, right? So then in the second like inference step, it has Sundar Pichai in its input, and it goes through the first layers. And so it can extract all the information for the second hop. So, I mean, definitely exactly what you said.
Thanks. Okay, so it looks like we have no other questions. Let's thank the speaker again. Also, I'm also thankful that you didn't get any, air raids.
Yeah.
Sorry that you couldn't make it. So we'll come back at 11:30 then. Thanks, everybody.